Welcome, everyone. Ready to dive into black holes. And they're even weirder cousins, gravastars.
Definitely, it should be fun.
We've got some great sources lined up. Kurzgesagt, National Geographic, even an interview with Brian Cox. No time to waste, though. Let's get right to it.
Yeah, let's go. Black holes. They're born when giant stars die, right?
Yeah, but it's more than just dying. It's like the star goes out with a bang.
It's true. We're talking stars way bigger than our sun, ending in a supernova. The core, if it's massive enough, it just keeps collapsing in on itself until, boom, black hole.
It's insane, like squeezing the sun into, what, a few kilometers?
Yeah, something like that.
And then there's that point of no return, the event horizon. I've always been curious, why can't even light escape a black hole?
Well, you see, it's about how gravity warps space-time. Think of it like a bowling ball on a trampoline. Creates a dip. Anything rolling too close, it falls in. Black hole's gravity, it's so strong it makes a dip so steep, nothing, not even light, can climb back out.
Okay, that makes sense. What about spaghettification? I read somewhere that it might be more like getting flattened like a pancake instead.
Yeah, that's right. Newer research suggests that you'd probably get squished horizontally before getting stretched out. So less spaghetti, more pancake.
Okay, either way, I think I'd rather stick to regular pancakes. So black holes have this image of sucking up everything around them. But they're also super active, right?
Oh, yeah, for sure. They can actually shoot out these jets of energy thousands of light years long.
Seriously.
Yeah, it's wild. Brian Cox said it best. The energy from a spinning black hole, it can outshine all the stars in a galaxy combined.
Wow, that's hard to imagine. Something that eats light can also be this powerful engine.
Which brings us to something I find really confusing. The black hole information paradox. Black holes seem to destroy information, but the laws of physics say that shouldn't be possible, right? Right. It's a tough one. Think of burning a book. Seems like the information's gone, but it's still there, in the smoke, the ashes. With black holes, it seemed like information vanished forever. Then came Hawking radiation.
That's the idea that black holes actually leak particles, right?
Exactly. And new studies suggest that information might be hidden in the way those particles are connected. So if we could decode that, we might get that lost information back.
So maybe black holes aren't the ultimate information shredders after all. But let's get to the really crazy stuff, gravastars. These are like the hypothetical rivals to black holes.
Picture this, a super dense, ultra-cold shell of matter surrounding a core of pure vacuum energy. That's a gravistar.
So instead of everything getting sucked in, some stuff might bounce off this shell.
Exactly. And that bouncing could make a cosmic echo that we might be able to detect. If we find those echoes, it could change everything we thought we knew about black holes.
Okay, I definitely need to hear more about gravastars.
Yeah.
But before that, how would one even form in the first place?
It'd be quite an event. Imagine the core of a dying star collapsing. And at the same time, this burst of vacuum energy pushing outward, they clash. And bam, you get this brand new type of matter squeezed to the absolute limit.
So we've got these theoretical gravastars. But how could we even know if they're really out there? Could we mistake them for black holes?
Well, it is tricky. Both black holes and gravastars would have really strong gravity, so just looking at how they pull on nearby stars wouldn't be enough to tell them apart.
So is there some kind of giveaway, something unique that would let us tell them apart?
Maybe. We can maybe find these echoes in the gravitational waves given off when gravastars collide. These echoes, they'd be totally different from what we see with black hole mergers.
Gravitational wave echoes, huh? I think I need to understand that better.
It's like, think about a rock skipping on water compared to just plop, one splash. That's the difference in the gravitational waves. The gravistar's shell makes those echoes, like skips in the signal.
So we can actually hear the difference, even though these things are billions of light years away.
Pretty much. And it's all thanks to, the progress we've made in gravitational wave astronomy. Instruments like LIDO, they're opening up this whole new way to observe the universe, letting us listen in on these crazy events.
So these echoes would be like proof, like finally saying, yeah, gravastars are real. That would totally change how we see the universe.
Oh, for sure. A complete game changer. But even if, gravastars turn out to be just a mathematical thing, just the fact that we're talking about this shows how far we've come.
It's like we're constantly pushing the boundaries of what we thought was possible, right? And speaking of that, I remember Brian Cox saying black holes are the key to understanding the universe. What did he mean by that?
He was talking about those fundamental questions, the ones about space and time and how the laws of physics work. Black holes, they really challenge our understanding of gravity, especially at the extremes.
And what's at the heart of this challenge?
The singularity, that point where everything gets crushed into, well, a single point, infinitely dense. It's where our current theories break down. We just can't make the immense gravity from general relativity work with the quantum world, the world of the super tiny.
It's like trying to jam a square peg into a round hole. We've got these two super successful theories, general relativity for the big stuff, quantum mechanics for the small, and when it comes to black holes, they just don't get along.
Exactly. And that's where the hunt for a quantum theory of gravity comes in. A theory that could bring those two worlds together and explain what really goes down at the heart of a black hole.
So black holes, they're not just fascinating in themselves, they're making us rethink some of our most basic ideas about the universe. They're like these cosmic labs, pushing us to the edge of what we know.
Yeah, like they're daring us to figure them out. And you know what's really interesting? Black holes, they're not just sitting there. They can be incredibly active, like shooting out those powerful jets of energy.
You mentioned they can even influence whole galaxies, right?
Absolutely. Those jets, powered by the stuff swirling around the black hole, they blast out for like thousands of light years, heating up gas clouds, even kicking off the formation of new stars.
So they're both destructive and creative forces.
Precisely. They gobble up stars and planets, but they also kind of seed the universe with the ingredients for new stuff to form.
It's like a cosmic recycling program.
That's a great way to put it. And it highlights how connected black holes and galaxies are. They grow and evolve together, influencing each other in this crazy cosmic dance.
We talked about supermassive black holes earlier, the ones at the centers of galaxies. But I'm curious, how did they get so huge? Did they form that way or did they grow over time?
That's been puzzling astronomers for a long time. There are a couple main ideas. One is that they were born early on in the universe, maybe from the collapse of giant gas clouds. The other idea is that they grew gradually, by merging with other black holes and just eating up stuff around them.
Like a cosmic nature versus nurture debate.
Exactly. And the truth might be a mix of both, you know. Some might have formed early on, others grew over time through mergers and all that.
So it's like those black holes hold clues to the history of their galaxies.
You got it. And each time two black holes merge, it's a massive event. Tons of energy released as gravitational waves.
Which LIGO and other detectors can now hear, giving us a whole new way to study the universe.
It's revolutionizing astronomy. Listening to those waves lets us trace the history of black hole mergers, map them out, and even put Einstein's theories to the test in the most extreme environments we know of.
It's like we're deciphering the symphony of the universe.
That's a great analogy. And speaking of symphonies, remember those gravastars? Think of the kind of gravitational waves they'd make when they collide.
Those echoes would be like adding a whole new instrument to the orchestra.
Exactly. A completely new pattern in the signal, unlike anything we've ever seen. That discovery would be groundbreaking, really making us rethink what we know about these extreme objects.
Okay, I am sold on gravastars. But let's switch gears a bit. What about wormholes and the holographic principle? Those always seemed like pure science fiction to me.
I know, right? But they're serious scientific ideas that came out of trying to understand black holes and space-time.
So first up, wormholes. Could these tunnels through space-time actually exist?
Well, they do fit into Einstein's equations of general relativity, so mathematically they could exist. The idea is that a wormhole could connect two really distant points in space-time, like a shortcut through the universe.
Like a cosmic subway system.
Yeah. And some theories say black holes might be the gateways to these wormholes, passages to other parts of space-time, maybe even other universes.
That's mind-blowing. So are you saying if we could somehow make it through a black hole, we could pop out in a totally different place?
Yeah.
Maybe even a different universe?
It's a fascinating idea, but we're still in the realm of speculation here. We don't even know for sure if wormholes are real, let alone if we could travel through them. But it's amazing that we can even think about these possibilities, right? It shows how far we've come in understanding the universe.
It definitely reminds us that we're always pushing the boundaries of what we think is possible.
Absolutely. And speaking of pushing boundaries, let's talk about another mind-bending idea. The holographic principle.
Oh, yeah, you mentioned that earlier. It's the idea that the universe is like a giant hologram, right?
Right. It suggests that all the information inside a region of space can be encoded on the boundary of that region. Like, imagine a 3D image projected from a flat surface.
Are you saying our 3D world might be an illusion?
That's the radical part of this idea.
Yeah.
It suggests that reality might actually be encoded on a lower dimensional surface, like the event horizon of a black hole.
Okay, I need a minute to process that. Well, how does this connect to black holes?
Well, black holes are super dense, and their event horizons are like these boundaries to the information trapped inside.
So if this holographic principle is true, everything that falls into a black hole, all the information, it's all encoded on the event horizon, like a cosmic memory bank.
Exactly. And this has huge implications for how we think about black holes and information. It suggests that information might not be destroyed when it falls in, but actually encoded on the event horizon.
Like a cosmic echo, preserving the memory of everything the black hole has ever swallowed.
You got it. And it might even solve the black hole information paradox. The information seems to vanish, but it's actually there on the event horizon waiting to be decoded.
It's like the universe is a puzzle, and black holes hold the pieces.
And the more we learn about them, the closer we get to solving it.
This deep dive has definitely given me more questions than answers. But that's what's so great about science, isn't it? The more we learn, the more we realize there's so much more to discover.
Exactly. And that sense of wonder keeps us exploring, asking questions, and pushing those boundaries.
So, to everyone listening, keep looking up, keep asking those questions, and never stop exploring. There's a universe of wonders out there.
And who knows what incredible discoveries are waiting for us out there. Thanks for joining us on this deep dive into black holes and gravastars.
Until next time, keep your curiosity burning bright. Okay, we keep talking about how black holes warp space-time, but I'm still kind of struggling to picture what that actually means.
All right, well, imagine, like, space-time as this giant sheet of rubber, okay? And you put a bowling ball on it, it's going to make a dip, right?
Yeah, I get that. The heavier the thing, the bigger the dip.
Exactly. Now, with a black hole, that dip gets so steep, it's basically like a hole in space-time. That's what we call the event horizon.
Right, the point of no return, where gravity's so strong, nothing escapes.
Yep, that's it. And this warping, it does some crazy things to time itself.
Wait, seriously? Time slows down near a black hole.
That's right. It's called gravitational time dilation, one of Einstein's predictions from general relativity. Stronger the gravity, slower time goes.
So if I was hanging out by a black hole, hypothetically, of course, time would be moving slower for me than for someone back on Earth.
Yeah, basically. You'd be traveling into the future compared to them. Of course, it's all theoretical. No one's getting close to a black hole and coming back to tell the tale.
Okay, so like natural time machines, in a way.
Yeah.
What about that bending light thing?
Right, gravitational lensing. Another effect of warped space-time. Imagine a black hole between us and a distant galaxy. Its gravity bends the light from the galaxy so it looks distorted, even magnified.
So black holes are like giant cosmic lenses messing with how we see the universe.
Exactly. And this lensing, it's not just pretty, it's a tool for astronomers. They can study things that would normally be too faint or far away.
So we can use black holes to study the universe. Wow. We've gone from these scary things to, like, scientific tools.
They're both, really. They remind us about the extreme stuff out there, and they push us to understand more.
It's amazing. Just a few decades ago, we weren't even sure if black holes were real.
And now we're talking about using them to learn about the early universe and maybe even figure out quantum gravity.
What a journey. And it feels like we're just getting started with black holes.
We definitely are. Still so much to learn, how they form, their role in galaxies, what happens to the information that falls in.
So many questions. This deep dive has given me more questions than answers, honestly.
But that's the beauty of science, right? The more we learn, the more we realize how much is still out there.
Exactly. And that's what keeps us going, that curiosity.
It really is. So to everyone listening, keep looking up, keep wondering, never stop exploring.
The universe is full of amazing things waiting to be discovered.
And who knows what we'll find next. Thanks for joining us on this deep dive into black holes and gravastars.
Until next time, keep that curiosity burning bright.